Hello everyone, welcome to APS Deep Academy and this is your mentor Swati Joshi. In last class we study about semiconductor materials and their properties. We also study why we prefer silicon more than germanium to make electronic devices. Now in this class we will study classification of semiconductors. Now classification of semiconductors, the semiconductors are broadly classified as intrinsic or extrinsic. Intrinsic semiconductors, we also call them as pure semiconductor, and extrinsic semiconductor we also call them as impure semiconductor. Now let us discuss intrinsic first. Let us consider silicon and germanium. If we using these both in their purest form, it means no impurity atom is added somewhere, then the crystal lattice of those silicon or germanium is considered as intrinsic crystal lattice or intrinsic semiconductor. We know that silicon and germanium, they both have 4 valence electron in their outermost shell. So they both have tetravalent structure. Tetravalent structure. Okay. Now, if I talk about silicon, silicon has a electron band gap Eg of 1.12 electron volt and germanium have band gap Eg of 0.72 electron volt. So, I am drawing a structure of silicon lattice here. Let us see, this is silicon lattice. We know that in outermost shell 4 electrons are there, 1, 2, 3, 4. In this also 1, 2, 3, 4 and this also 1, 2, 3 and 4. Now we can see that each silicon atom is bounded with another silicon atom with covalent bond here. This is the covalent bond. Means no electron or no hole is free or extra here to take part in conduction. It means this bond is these atoms are bounded with each other, so no free electron here. If I make the electron free, I need at least 1.12 electron volt to give to this structure of semiconductor and make this electron free to take part in conduction. So intrinsic semiconductor have low conductivity than extrinsic semiconductor. The major application of extrinsic semiconductor is this only, that we do doping process. We increase the free electron or hole concentration so that the conduction increase. And yesterday class we also study the resistivity also. That is a property of semiconductor, that we can change the resistivity by doping. So this is the structure of intrinsic semiconductor, that no free electron is there, no free electron. If I make this electron free from this bond, we have to take at least 1.12 electron volt in case of silicon and 0.72 electron volt in case of germanium. Now let us see extrinsic semiconductor. Okay, extrinsic semiconductors are impure in nature, means we have to give some impurity to them to increase to make change in their lattice structure for increase the conductivity and change the resistivity as well. So extrinsic semiconductor are of two type, one is N-type, one is P-type. Okay, now let us discuss in detail what are those N and P-type. So if I talk about impurities, we also call them pentavalent and trivalent. Pentavalent and trivalent. Okay, if I consider pentavalent impurity, or I am doping pentavalent impurity with any silicon or germanium or semiconductor atom, then we consider those as N-type. It means the majority charge carrier in this is electrons. If I am doping it with trivalent impurity, then we consider those as P-type. It means majority charge carrier in this lattice is holes or positive charge or empty space. Hole can also consider as positive charge as well as empty space. Okay, now pentavalent impurities are group 5 element. Group 5 element of periodic table are phosphorus, arsenic, antimony and bismuth. And similarly, group 3rd element of periodic table are boron, indium and gallium. Okay, now let us draw the structure of N-type semiconductor. So I am considering the antimony here. This is the atom of antimony. So antimony have 1, 2, 3, 4 and 5 electrons in outermost shell. So it is pentavalent impurity. Now silicon, silicon, silicon and silicon. 1, 2, 3, 4. So they bond with silicon, but one electron is left. Here we can see covalent bond. These 4 electron of antimony is bonded with silicon atom, but this electron is free. It is not bounded with anyone. So this free electron can create take part in conduction, and it is a majority charge carrier, and this is an N-type semiconductor. Okay, so we can say that this electron as donor also. Okay, this electron is donor also. It means this electron, um, it means the lattice try to donate this electron so that it will combined with another covalent bond or another bond, so that the structure of this lattice will complete. So this electron has tendency to take part in conduction. It wants to join another atom, so the bond will create. So this is called as donor atom. It means the lattice is donating this atom to outer side, so that this will take part in conduction or else create a bond. So we create this because we need the conductivity increment in intrinsic semiconductor. So this electron has to take part in conduction because this is a free electron here. So this is the structure of N-type semiconductor. Let me show the band diagram of N-type semiconductor here. So this is the band diagram of N-type semiconductor. This is valence band, this is conduction band, and near to conduction band we have donor level, because this N-type impurity because the lattice need to donate this N-type impurity and take part in conduction. So this is the band structure of N-type semiconductor. Okay, now let us discuss the second one, P-type semiconductor. Similarly, like N-type semiconductor, in P-type semiconductor, 3 electron bond with silicon atom, but one extra space or positive space, positive charge or hole is created. Let's see here. If I talk about boron, so boron have 3 atoms, 3 electrons, 1, 2, 3. So 1 silicon atom, 2 silicon atom, 3 silicon atom, let's consider 4 silicon atom. So these 3 creating covalent bond with this, but we can see that here no electron is there, so a vacancy is created. This is positive charge or hole here. It means this what this hole is doing, this hole is nothing but it is accepting electron from somewhere else. So this is the acceptor level or A level, we can say. This space is empty every time, so that any electron from anywhere in the lattice can try to jump and fill this space. So this is the part of conduction in this lattice. So the process of conduction is increasing, and the majority charge carrier is hole here, which is positive charge or an empty space. So if I talk about the band structure, then we can say that this is valence band, this is conduction band, and this is the acceptor level near to valence band. Now there are so many applications when we do when we apply the impurity here. Okay, one thing you need to know here, the term doping. Doping is nothing but doping is putting the impurity atoms into the lattice. So doping is nothing but we dope semiconductor with some trivalent or pentavalent impurities. So doping is term which is used for this process of giving the trivalent or pentavalent impurity to the lattice structure. So I think the topic is clear for today. Today we do classification of semiconductor. Intrinsic semiconductors are uh, very pure, extremely pure condition of semiconductor, they doesn't start conduction by themselves. We need to give at least 1.12 electron volt in case of silicon, and 0.72 electron volt in case of germanium to break the bond and the electron take part in conduction. And in extrinsic type, we dope with N-type and P-type impurities. N-type impurities simply pentavalent impurities, and P-type impurities are trivalent impurities. Trivalent means in outermost shell 3 electrons are there, which are group third element of periodic table. Pentavalent means in outermost shell 5 electrons are there, which are group 5 elements of periodic table. If we dope this with silicon or germanium to make extrinsic semiconductor, then we have to do a process of doping to put the impurity into the atom to increase the conductivity of a particular crystal lattice. So this is all about classification of semiconductors. Now I will see you in next class. Thank you.